Good afternoon. Welcome and thank you for watching our 30% design presentation. We are Team Fish, students of St. Martin's University. Our mock project was provided by Thurston County Public Works using their geotechnical and survey data for a recent fish passage replacement at the intersection of Thompson Creek and Thompson Creek Road. My name is Edward Supis. I'm part project manager, part designer.
My name is Jeffrey Lowe, and for this semester, I am acting as the team leader, focusing on assigning tasks and keeping the team on schedule, as well as developing an environmental plan for this project.
Hello, I'm Abraham Dabaso, and I'm the lead drafter.
In Washington State, fish barrier removal efforts really began in 1991 when the Fish Passage Barrier Removal Program was created. A fish passage barrier is defined by WSDOT as anything that hinders fish from moving upstream or downstream. Some of these obstructions could happen within existing water control structures, such as culverts and dams. Luckily, there are several progressive engineering methods available that can help mitigate some of the hazards inhibiting the journey of our scaled friends. Large dams, such as the Bonneville Dam on the Columbia River, have an engineered solution to the fish migration problem in the form of a fish ladder. Small dams like the one in my neck of the woods on Chambers Creek has this system incorporated as well. The effectiveness of this method has a mixed record of success, though, and leaves much room for improvement. But for the purposes of our project at hand, it's important to define the structure that is arguably the most common form of fish barrier. Culverts are pipes that can be any number of different sizes and made from a diverse multitude of materials. They're designed to allow water sources like streams, creeks, and stormwater to flow from one side of a roadway to another. Problems arise in many different ways. A lot of them have been designed only for water diversion, without the foresight of the water's inhabitants' need to traverse the aqueous system. A hydraulic design can be constructed with the velocity of the water so high that the fish wishing to migrate upstream have little to no chance of conquering the current. Or the culvert can be at the top of an inclined slope where the path of the fish is too high and the animal's vertical movement ability is not great enough to attain the altitude required. The depth of the water in every stage of the fish's journey also has to be considered in order to maximize the chances of a successful aquatic expedition. If the depth of the pool before the culvert is too shallow, the fish will have trouble jumping into the passage. If the water inside the culvert is too shallow, the fish will be thwarted by the lack of the aqueous medium needed for its specialized method of locomotion. As you can see here, the most obvious characteristic of the Thompson Creek culvert that classifies it as a fish barrier is the lack of water depth. The stream undercuts the 11-foot diameter pipe and is now flowing through a crevice underneath the culvert, making it impossible for fish to navigate this passage if there is not a substantial excess of water flowing through it. The purpose of this project is not to focus on the preservation of one particular species, or even a specific genus for that matter. The benefits that precipitate from a little planning and action by attending to the requisites for an unhindered fish passage are numerous. The passages are a necessary component for propagation and population growth. Fish are an important food source for upwards of 100 kinds of wildlife, including our own species, especially the pescatarian faction of humanity. They are also an important aspect of Washington State's economic health through both commercial and recreational fishing. According to WSDOT.gov, an estimated 16,000 jobs and over $500 million in personal income are supported by these activities. And they are only possible through a prospering fish populace.
The goal is to design and construct an improved bridge structure on Thompson Creek Road.
This is the map location of the project, mapped with Google Maps. It is located within Tenino, Washington's city limits. To the south, and if you look at the map on the top right, it is to the east of Centralia. Our crossing follows criteria set forth by design specifications, standards, design manuals, government and city policies and guidelines, and design code. The primary sources were Thurston County Public Works and Washington Department of Fish and Wildlife. A couple notable design requirements are: 1. Abutments, piers, pilings, etc. shall not restrict the flow so as to cause any appreciable increase up to 0.2 feet in backwater elevation or channel-wide scour using the calculated 100-year flood. The span and width must be designed in regard to the fish species present for passage and habitat. 3. Minimize disruption to the stream bed. 4. And we found that a reach analysis will likely be required for this crossing. And 5. The low chord of the bridge must be at least 3 feet above the 100-year flood.
One of the most invaluable tools and resources for this project was the Washington Department of Fish and Wildlife Water Crossing Design Guidelines Manual. It includes extremely helpful sections such as culvert bed design, bridge design guidelines for habitat protection, fish passage requirements, crossing site considerations, channel profile adjustment, and so much more.
The provided geotechnical report was completed by Landau Associates, with the 2 boring hole locations shown on the left picture. They reported distinct layers of fill, alluvium, and marine sedimentary rock. Based on the conditions, recommendations and design parameters were given for retaining walls, seismic design, earthwork, and construction. Notably, the existing roadway, gravel, fill has the right properties and near optimal moisture content during the summer, which is where they like to build it, to be reused as embankment fill on the construction site. The marine sedimentary rock has good bearing properties that are ideal for a shallow foundation and is the recommended alternative presented. Deep foundations are possible, but point bearing capacity was ignored due to the presence of coal in the rock. The following design parameters were given for resistance and bearing design that you see in the tables. An alternative analysis was completed to decide between shallow and deep foundations, falling in favor of shallow foundations. It was found that shallow foundations were cheaper to construct, considering both material and construction costs. It would also be more constructible, as deep foundations would require large machinery to drive the piles. However, deep foundations may require less material transportation, though it doesn't outweigh the other costs. Both are equal in longevity and potential salvage value. The 5 listed crossings were considered. Concrete box culverts were a good option, but it was decided against due to the lack of available height in comparison to the length suggested by the client, and for accommodation of river movement. This is the same reason against a steel pipe or a pre-stressed concrete arch, shown in pictures 4 and 2. The more likely option were pre-stressed concrete girders and steel girders for a more conventional bridge design that would allow for a wide channel design. The pre-stressed concrete is the best option as it is less susceptible to wet climate and is highly used in bridges in Washington, and therefore would be a readily available and potentially cheaper option. The following is a spreadsheet of the budgeting that we've done so far for a concrete girder bridge. And as you can see on the top, the total estimated cost is $342,000. Ultimately, the crossing that was chosen was a through arch bridge with the arch above the span, not because it was the best alternative or what the client would want in a real-world situation, but because it would be an interesting thing to design. With the arch on top taking compression, it can be either steel or concrete. The beam would be a steel tension member that is connected to the arch to take its compression. Then there would be cables coming down from the arch to the beam. It could still be supported by shallow foundations. If you see in the section view, you could have 2 eye girders on their sides for better lateral stability. And then you'd have a steel or concrete floor beam, and we could have concrete decks on top. So potentially it could be all precast and very minimal construction. It would only be assembly required for the bridge support. And maybe you could get it in with only 2 trucks. Since everything is smaller and you could weld or bolt the top of the arch together, you could have smaller cranes because your beams are not as large. This would also give you a better water clearance. And this would very much explore the topic of accelerated construction techniques. The risk analysis have been a potential design change if the contractor suggests a cheaper material or a slight alternative to a part of the design, or discovers that conditions are different than expected or accounted for. Second, the potential change in decision in design if the client has a change in objective or criteria. Delay or redesign to meet satisfactory with tribal and public authorities or concerns if occurring later in the design phase. All three were seen as unlikely due to the small scale of the project and potential for change. The project is already part of a tribal organization for the improvement of fish passages.
The construction phase of the proposed fish passage project presents several potential environmental risks. There is a possibility of pollutions, as the construction process could lead to the release of pollutant into the nearby surrounding and the streams. This poses risks to water quality and the aquatic ecosystem. Habitat destruction is another concern, as the replacements of the existing culvert and the constructions of the new bridge may disrupt the surrounding ecosystems, impacting the local plants and animals. The alternation of the stream during construction process risks of habitat disturbance, and additionally, the construction could introduce obstacles that may temporarily obstruct fish migration, affecting their natural movement. Given those potential risks, it is crucial for the project management team to implement a healthy environmental safeguard and a migration measure to minimize pollution.
One of the essential steps in planning for the removal of the old culvert and the construction of the new passageway is developing the SWPPP, the Stormwater Pollution Prevention Plan. It's a crucial step in obtaining the proper permits by appeasing both the EPA and the Washington State Department of Ecology. The steps for developing this plan are site assessment, selecting the relevant erosion and sediment control BMPs, selecting good housekeeping BMPs, planning for inspections, maintenance, and record keeping, and finally, implementing the plan. Another thing to consider is developing a stream bypass while the construction is taking place. In one of WSDOT's barrier removal projects located in Snohomish, shown here, a very involved effort was required that included constructing a temporary access road along with pumps and temporary damming required for that bypass. After the construction is completed, the last step is stream bed restoration. This could include things such as stream buffers, stone placement, and revegetation work to help ensure that the fish will forgive our naive human transgressions, accept the new passage as our apology, and use it to migrate and multiply.
This is our schedule that was arranged at the beginning of the year. So far, we've kept it on track fairly well. The only item that is behind schedule are the preliminary drawings to be submitted with 30% submittals. Though luckily, it was an internal deadline, and we still have time to get it completed before it's due. The schedule is shooting for 100% design by the end of the year, though if we end up designing for the superstructure, substructure, detour, and the river improvements, we may shoot for a 60% submittal because of the small design team. The next step is to design the river improvements and the bridge crossing. Design a 30 to 90% with the associated cost, estimates, plan sets, and reports, then to the 100, hopefully, with final designs, plans, specifications, and its cost estimates. Thank you for watching. Here is the link to the relevant project files presented for review on a Google Drive.